Welcome back to the energy conversion lectures. In previous lectures, I have provided some hints about the equivalent magnetic circuits. In this lecture, I will provide more details about the equivalent magnetic circuit and its analogy with the electrical circuit. Let's start with some comparison between a simple electrical circuit and a simple magnetic circuit. The electrical circuit consists of a voltage source E or electromotive force EMF and a resistance R. The EMF produces or drives an electrical current I against the electrical resistance R. The electric current of this electrical circuit can be determined by applying Ohm's law as follows. R is equal to L over rho A. As you can see, the resistance R can be calculated based on the length of the resistance L, material conductivity rho, and the cross-section area of the resistance A. Now let's look at the magnetic circuit. This magnetic circuit consists of a coil, current, and magnetic material core. We learned from previous lectures that the magnetomotive force MMF or the ampere turns Ni produces and drives a magnetic field lines phi against the magnetic reluctance R of the medium. It is very clear that the ampere turns Ni is like the EMF of the electrical circuit, and the reluctance R of the magnetic circuit is like the resistance of the electrical circuit. Also, the magnetic field lines phi is like the electric current of the electrical circuit. Based on this analogy between the electric and magnetic circuits, the magnetic circuit can be represented by an equivalent circuit called equivalent magnetic circuit. The purpose of developing the equivalent magnetic circuit in practice is to calculate the magnetic field lines phi if the ampere turns Ni and the reluctance are known. It should be noted here that Ohm's law and other important electrical laws such as Kirchhoff's voltage and current laws that apply to electrical circuit can also be applied to the equivalent magnetic circuit. Based on the analogy with the electrical circuit, Ohm's law of the magnetic circuit can be represented as follows. Also, the reluctance of the magnetic circuit will be equal to L over mu A, where L is the mean length of the magnetic path, mu is the permeability of the medium, and A is the cross-section area of the medium. Basically, these new formulas of the magnetic circuit have been driven using the analogy between the electric and magnetic circuit. These formulas can also be confirmed by using the following relationships. As you can see, the relationship between Ni, phi, and reluctance R matches and confirms what I explained earlier. It is very clear from the formula of the reluctance that the reluctance R is directly proportional to the mean length of the magnetic field path L and is inversely proportional to the cross-section area A and the permeability of the medium mu. In general, for any equivalent magnetic circuit, the coils and currents are converted to MMF, and any medium must be considered and converted into a magnetic reluctance R. The medium could be a magnetic material or non-magnetic material such as air. Now assume we have the following magnetic circuit. This magnetic circuit consists of 3 different magnetic materials with different lengths. The equivalent magnetic circuit can be drawn as shown. Basically, the magnetomotive force F, or the ampere turns Ni, represents the source of the equivalent circuit that drives or produces the magnetic field lines phi. Each section of the magnetic circuit has its own reluctance because they are from different magnetic materials and have different lengths. Basically, if the length or the permeability or the cross-section area of the medium sections of the magnetic circuit are different, means we have different reluctances. Another important note is that the magnetic field lines phi is same for any series magnetic path in the equivalent magnetic circuit. However, the magnetic field densities B of the series magnetic path are same only if the cross-section area of the magnetic path are equals. In other words, if the cross-section areas of the reluctances are different, the magnetic field densities are different as well. Another important note is that the total magnetomotive force or the total ampere turns Ni will be distributed across the reluctances. The higher the reluctance medium will require higher ampere turns across it, comparing with the low reluctance medium. These distributed ampere turns are like the voltage drop across the series resistances of the electric circuit. Now, based on what I have explained, the total ampere turns will be equal to the following. Since the magnetic field phi and the cross-section area A are same for all magnetic circuit sections, the magnetic field density B for this equivalent magnetic circuit is same through the 3 magnetic materials and is equal to the following. Let's assume we have the pH curves of the 3 magnetic materials of the magnetic circuit as shown. We can find the magnetic field intensity H for each of the core materials for the calculated magnetic field density B. By applying Kirchhoff's voltage law, we can calculate the total ampere turns Ni as follows. The current required in the coil can be calculated as shown. Based on the information we have, we can also calculate the permeability and relative permeability of any sections of the magnetic circuit. For instance, the permeability and relative permeability of the nickel-iron alloy can be calculated as follows. Now let's see how to draw the equivalent magnetic circuit for some electrical rotating machine. This magnetic circuit in this example represents a basic structure of a synchronous machine. The steps to draw the equivalent magnetic circuit are as follows. First, draw the magnetic field paths. Second, find the MMFs and the reluctances along the magnetic field lines. Then draw the equivalent circuit. It should be noted here that the relationships and calculations of the magnetic circuits in this and previous lectures are developed and performed under some assumptions and approximations. These assumptions are: first, assume all magnetic field lines are confined within the magnetic core. Second, the magnetic field lines are uniformly distributed on the cross-section area. And third, the relationship between the electric current and the magnetic field linkage is linear. Before ending this lecture, let's review the main rules used to solve the equivalent magnetic circuits as follows: reluctances in series, reluctances in parallel, Kirchhoff's voltage law, and Kirchhoff's current law. Now let's conclude this lecture at this point and we'll continue in the next lecture. Thanks for listening. I am Ihsan Al-Nabi and it was a pleasure sharing this lecture with you. Thank you.